Hello everyone. The topic of this lecture is going to be panel data. You will need two packages for this lecture. You need PLM and LM test. Note that the package OpenXLSX, you should have already installed it on your computer. Also note that on Canvas there's an Excel file called paneldata.xlsx and you are going to need this Excel file. Note that there's also documentation online for this lecture or for the packages used in this lecture, and you can access those supplemental information by clicking on the link. So the topic of today is panel data, and before I continue, let me explain what panel data is. And in order to do so, I'm going to use a graph or a table. Now, what we have seen so far is the following. So far, we had what is called cross-sectional data. Okay? So cross-sectional data, imagine the following. Suppose you have individual. Suppose you have individual A, B, C, D, and E. Okay? And we just looked at one time period. Okay? And suppose we just said that it is in time period t equals 1. And we had, for example, data on individual A about the salary. Okay, so assume it is, say, $40,000. Individual B, we had $30,000. C had, say, $60,000, and so on. Okay, so we had data about, in a particular time period, about individuals. Now, when we are looking at panel data, we are going to have data about individuals, but we have those data sets for multiple periods, okay? Say for T2, T3, and T4, okay? Where T represents the time period. So for example, we have the first person in time period 1 had a salary of 40,000. In time period 2, suppose that person now has $41,000. And person B had in time period 2 now has, say, $33,000, and so on. Okay? So what we have seen so far is cross-sectional data. So we just looked at one particular time period. Okay? So for example, if you're thinking back about your last homework on the data about hybrid vehicles, we just looked at the decision in one particular time period. Note that very often that time period isn't even explicitly specified. Now in a panel data set, we have, besides the individuals, we now also have time periods. Okay? Now note that panel data is extremely difficult to collect, because what it requires is that you are observing the same individual. Okay? So in this case, it would be individual A, and you need to collect data not only in one time period, but you have to collect data over multiple time periods. Okay? Now, panel data set is very useful in the case if you want to explain, for example, how students from elementary school all the way to high school, how they actually evolve over time. Okay? Or for example, or how their performance, how their grades evolve over time. Okay? Okay, now there are two types of data when we are combining cross-sectional data with a time component, okay? And what I presented you before is the second part, is basically the panel data, a true panel data set, okay? However, you can also have what is called pooled data, where you have a combination of multiple cross-sectional data over time. So, for example, you all remember the data set that I'm using in class about the General Social Survey, GSS. Okay? As you remember, the data is collected over multiple years. and always asks the same question. So, for example, if you go on the GSS webpage and you look at the question associated with total family income, okay, then you can see that this question of how much was your total family income was asked every year between 1973 and 2018. Note that here this is pooled data in the sense that the same question was asked every year. However, the person who answered the question or the household who answered the question changed from year to year. Now, this has the advantage that you do not have to follow a particular person between 1973 and 2018. Now, this would be an example about pooled data. Okay? For example, a second example would be if I'm looking at grades in this class, say if I'm looking at either statistics V507, this class, or the regular statistics class, V506, or even my economics class. If I compiled data about the grades of students based on their concentration, then that would be pooled data, because I'm not observing the same student from in one semester, and that student changes then in the next semester. Okay. A third example would be the American Community Survey, who is also asking the same questions in multiple time periods, but it is not the same individual answering the question. Now, true panel data is if we have a repeated measurement or the same question of the same individual over time, okay? And again, note that this data is very difficult to collect. The individual units can be people, can be states, can be firms, counties, countries, etc. Now, there is one national example, which is called the National Longitudinal Survey. So, for example, you can go on this webpage, and then you can have, for example, you can click on accessing data. You can go on investigator, and you can search as a guest. Okay? So this is a data set that collects data of individuals that were born in 1979. Okay? You can search variables, and for example, you can go on income, summary measurement, and net family income. Here you have data now that started in 1979 all the way up to 2016, and it tracks the income of a particular individual or of a particular household over time. Okay? Now, today we are going to look at how to analyze this data. We need special models because what we now have is that the error term that is associated with our regression analysis is now related over time. Okay? Remember that one of the assumptions of the ordinary least square models is that the error term is unrelated with each observation. But now, in this case, since we are talking about a particular individual being observed over time, the error term in, say, time period 2018 is most likely related to the error term in time period 2017. Okay? Now, there are certain assumptions about a linear panel model. First of all, we have to assume that we have regular time intervals. So, for example, we have monthly data or we have annual data. We also have to keep in mind that our errors are correlated and that some parameters may vary across individuals or across time. Now, we have seen so far that the intercept is usually not very important when we are talking about ordinary least square models. In this case, the intercept, or in the case of panel data, the intercept actually becomes very important, because the intercept captures effects that are specific to the individual and do not change over time. So, other examples of true panel data is, for example, the panel study of income dynamics, which collects data of about 5,000 families, and the data includes various socioeconomic and demographic variables. There's also a survey about income and program participation, and again, here the focus is on the economic conditions. And note that the advantages of those panel data sets are the following. You can better understand the dynamics over time of a particular individual, of a particular unit of observation, and you can also tease out the heterogeneity or the differences among observational units. And again, it is a combination of cross-sectional data with time series data, leading to more complete behavioral models. Now, there are two concepts that are related to panel data, and those are balanced versus unbalanced data sets and short versus long types. Okay? Now, in a balanced data set has the same number of time series observations for each subject, whereas an unbalanced panel data set does not. As you can imagine, the problem with panel data set is that certain peoples are going to drop out of the panel over time. This may be because of survey fatigue or death, for example. Now, when we are talking about a short versus a long panel data set, then a short panel has a larger number of subjects or observational units than their time periods. A long panel set has a greater number of time periods than observational units. Now, there are multiple types of regression models, and the first model is the simplest one, where we are looking at a pooled ordinary least square models. What this means is that we ignore the time aspect of the model and simply assume that all of those observations happen in the same time period. The two models that are listed here, fixed effects model and random effects model, are true panel data models, okay? And we will analyze them in this lecture. Now, let me give you an additional example about the pooled ordinary least square model. Remember that before I was talking about economics students or students in my economics class over multiple semesters. And suppose that I want to know how they perform in my class based on their concentration. Now, since the students change from semester to semester, what I could be doing is running a pooled ordinary least square model, in the sense that I take data from, say, 2014, 2015, and 2016, and ignore that those are 3 different years, and simply pool them all together in one particular year, or in one particular model. Now, this is what we are going to do on the next slide. Now, for this model, we are going to use the dataset Fertile1, which is part of the Excel file that I mentioned before. And note that this is data from the General Social Survey for the years 1974 to 1984. I know that the dataset is a little bit dated, but it will get the point across. So the dataset contains the following data. It has all the even years between 1972 and 1984. And the dependent variable which we are interested in is the fertility rate, or the number of children born. That would be the variable kids. Okay? But we also have data about the years of schooling of the mother. We have the education of the mother and the father. We also have data about the locality, whether they lived on a farm, in other rural areas, in a town or a small city. Note that this data is taken from the book Introductory Econometrics from Jeffrey Wooldridge. Now let us switch to R. Note that I have already loaded the data, and the dependent variable that we are interested in is the number of kids. Okay? We have education, we also have age, and we also have yearly dummy variables. Okay? So note that to specify year 1972, that we do not have year 1972 in here because it is considered the base year, in the sense that for if 1974, 76, all the way through 1984 is equal to 0, there's no 1, and hence we know that it is 1972. Okay? Now note that compared to the slides, we are going to construct a slightly abbreviated model here. But what you will see is, although that we are excluding many variables that are not in the slide, that are in the slides but not in this model, we still get very similar coefficients. So the model we are going to estimate goes as follows. We say B hat equals LM, and we are interested in kids, so the number of children born to a woman. Depends on education, age squared. Okay, so here we have a nonlinear term. And then we are going to include dummy variables. More specifically, we are going to include the yearly dummy variables. Okay. So 1974, 1976, 1978, 1980, 1982, and 1984. And the data is filter 1. Okay. So we run this model. Actually, this is B hat. We run this model. We say summary. And now what we see is the following. Okay. Now note again that this specifies the number of children based on education, age, and dummy variables indicating the year. Now we see that education is negatively related to the number of children, and that age is, at first, we have a positive effect, so with increase of age, the number of children increases, but at a decreasing rate, because we have a negative here. Now, what is more important is that in 1982 and 1984, so in the early 80s, we have negative coefficients, and those negative coefficients are also statistically significant. This indicates a drop in the fertility rate over time. And note, what is important here is that this drop in fertility cannot be attributed to an increase in education over time, because we are controlling already for education. So education is already in our model. Okay? So here on this slide, I have the more complete model, and note that the coefficients are very, very similar, in the sense that for 1982 and 1984, I have 0.42 and 0.55, whereas on the slides with more variables included, I have 0.41 and 0.56. Okay, so those are very, very similar. Okay. So when you are controlling now for the observable factors, you see that the fertility rate has dropped over time. It is important to note that all those results are relative to the base year of 1972. Okay? So the coefficient associated with the fertility rate, or with our model in 1982, which is negative, indicates that a woman on average had 0.41 less children compared to 1972. Okay? And again, the drop is independent from education, since we are controlling for education, which is explicitly in our model. Okay? The second example, which I would like to cover, is from the current population survey. And again, this is slightly older data from the book that I mentioned before, and it is for data between 1978 and 1985. Okay? Now, here we will see that we can interact yearly dummy variables with key independent variables to see whether the effect of those variables has changed over time. In this particular model, we would like to explain how the wage somebody earned has changed between 1978 and 1985, and how this relates to education as well as female. Okay, so in the sense that we are going to look at the gender pay gap here. Now note that Y85 is simply a dummy variable that is coded as 0 if we are talking about the year 1978, and that is equal to 1 in the year 1985. So the interpretation of those coefficients is that beta 0 alone is the intercept in 1978, Y0 plus beta 0, this is gamma 0 plus Y0 is the intercept in 1985. And we have also the return to education in 1978, which is measured by beta 1. And the return to education in 1985 is measured by beta 1 plus gamma 1. Okay? So if we estimate the model in R, okay, note that again we have loaded the data in CPS 7885. We can estimate the following model. We can write B hat equals LM, and we have the logarithm of wage. Note that the logarithm of wage is already coded in the dataset as L wage, so which is the dependent variable, and the independent variable is Y85 plus education plus Y85 times education plus experience squared plus union plus female plus Y85 times female. And the data is equal to CPS 7085. Then we summarize the data. Now the interpretation of the data goes as follows. So note that education is measured in years and that the wage is taken as the natural log. So what this means is that for an additional year of education, we interpret this coefficient as a percentage change, of the wage. So what this model means is that the return to education in 1978 was 7.47%, okay, which is this coefficient highlighted here. Now, the return to education in 1985 is the 0.0747% plus the coefficient of 1.85, which means that the return to education in 1985 was 9.32%. Now, what is more interesting is that this is a model which can analyze the gender pay gap. Note that the coefficient for female is negative 0.32. What this means is that in 1978, the wage of a female was 32% lower compared to a male. Now note that in our model, we have also created an interaction between the yearly dummy variable 1985 and female. Okay? So beta 5 measures the pay gap in 1985, whereas beta 5 plus gamma 5 measures the pay gap in 1985. Based on our results, we can see that the pay gap has decreased. The coefficient in 1978 was negative 0.32, and the coefficient associated with the interaction term was 0.085. What this means is that in the year 1985, the pay gap between a male and a female was 23.5%. Okay. So you can see that this type of model can be very useful to analyze differences over time. Note that here in the slides you have the output of the model as well as the interpretation of the coefficient estimates. So one of my favorite examples in this class is again using very old data about home values near the location of a garbage incinerator. Here the story goes as follows. We have data about the home values in a particular town in 1978 and in 1981. Now, after the data was collected in 1978, a garbage incinerator was built in the town, and we have data about 1981, and we can estimate the effect of the garbage incinerator on home values. Now, it is very important for this example to realize that the data in 1978 was not influenced by the garbage incinerator, because nobody knew about the garbage incinerator in 1978. Okay? Now, the data which I'm going to use for this example is in Kiel, where you have data about between 1978 and 1982, and you have the price of homes. You also have information about the rooms, the lot size, area, bathrooms, and so on. And more importantly, you have data about whether the house is near the garbage incinerator. I cannot remember the radius in miles, but think about this as a dummy variable that indicates whether the home was close to the garbage incinerator. Now note, you may ask, how be that the dummy variable associated with the incinerator is also available for data for 1978. Note that although we have data about those homes in 1978, we do know whether those homes have been located near the garbage incinerator in the future. Okay? So let us estimate a very simple model and think about this as a naive model. So what we do in the first step is we subset the data, and we just look at homes in 1981. Okay? So we say subset here, year in 1981. So now here we have data about the home values only in 1981. Now, somebody not familiar with statistics could estimate the following model. B hat equals LM. Our price is the real price corrected for inflation. Our price tilde near incinerator. And the data would be Kiel 81. So you run this regression model, you summarize the results, and what you would find is the following: that homes in 1981 that were near the incinerator are valued on average almost $31,000 below homes that are not near the incinerator. What you could say is that the incinerator in this case had a negative impact and decreased home values by almost $31,000. Now let us repeat this exercise. Let us repeat it with data for 1978. So here we simply change 81 to 78. Right? And note, since we know where those homes are in 1978, we know where the garbage incinerator where the garbage incinerator is going to be. We can estimate the model. And here what we find is the following: that in 1978, homes that were located near the garbage incinerator, which didn't exist in 1978, are priced at almost $19,000 below the average value. Now, to tease out the effect of the garbage incinerator on home values, let us run the following model with the entire data set. Let's call it B hat equals LM, the R price, tilde, Y81, plus near incinerator, plus year 81 near incinerator. And we are using the entire data set. Now, what you have run here is what is called a difference in difference estimator. Okay? So note that we have an intercept, 82,517, which is the average home value of homes not near the garbage incinerator. 18,790 is the average change in housing values for all homes between 1978 and 1981. The coefficient of 18,824 is the location effect not due to the incinerator. And only the 11,864, or the negative 11,864, is the decline in housing values due to the incinerator. You can also get that value if you are subtracting 30,000, if you're taking the difference between 30,688 and 18,824. Okay? Now, this regression model shows that you have to be very careful in running a regression model and interpreting the values. Running the regression model simply with the data in 1981 and claiming that the incinerator destroyed home values by almost $31,000, in this case, is not correct. Now, let us turn our attention to real panel data models. Now, the data we are going to use for this example about panel data is going to be called Grunfeld. Note that although this is a very old data set, it works very, very well to illustrate the theoretical and practical concepts of panel data. Note that the data automatically comes with a package PLM, which you have downloaded and installed on your computer before. Note that the data contains information about 10 companies over the years 1935 to 1954. Specifically, we have data about the investment activity of the firms, we have data about the value of the firm, and we also have data about the capital stock of the firm. Now, for this exercise, we are just going to focus on 4 firms: GM, US Steel, GE, and Westinghouse. In the data set, those firms are coded 1, 2, 3, and 8. So when you look at the data in R, what you can see is that you have 5 columns. You have the firm, you have the year, you have the investment activity of the firm, you have the value of the firm, and also you have the capital stock of the firm. And suppose that you are interested in determining the investment activity of the firm as the dependent variable based on the independent variables of value and capital. Now, what you could be doing if you didn't know anything about panel data is to simply run a regular OLS model, where you ignore that we are talking about different firms and different time periods. So you would simply run a regression with investment as the dependent variable and value and capital as the independent variables. Now, the problem with this pooled OLS model is that it ignores heterogeneity among the individual firms and also across time. Okay? To fix this problem, we are going to estimate a panel data model that is either called a fixed effects panel data model or a random effects panel data model. So we are only interested in firms 1, 2, 3, and 8. So let's start subsetting our data to only extract those firms. So we write Grunfeld equals subset Grunfeld, comma, firm in 1, 2, 3, and 8. So now we have a data set with 80 observations, and we have only the firms of interest to us. Now, before we start preparing the data for a panel data set, let's just run a simple OLS regression. You write b hat, let's call it simple OLS, equals lm, investment as a function of value and capital. And the data is Grunfeld. Note that since I have two Grunfeld datasets, one with a capitalized G, one with a lowercase g, let me make sure to delete the dataset we do not need anymore. This will cut down on errors. So when we run the b hat simple OLS and we summarize the data, what we will see is we get our coefficient estimates, which describes the investment activity of the firm as a function of value and capital. And we see that both value and capital are determining the investment activity because they are both statistically significant. To run a panel data set with R, we have to prepare the data to let R know that we are talking about panel data. To do this, we write Grunfeld equals pdata frame. Note that this is associated with the package PLM, which you should have installed and loaded before. And you write Grunfeld, comma, and then you say index is firm, comma, year. Note that the data set now has row names that indicate the firm and the year. Now, in the first step, let us use the functionality associated with the package PLM, and let us run a panel data set. More specifically, let us run a pooled panel data set. Now note, when we are using the option pooled, then what we are doing is we run the identical model as before, where we ignore the panel structure. To do this, we say b hat, let's make it specific that we are using the PLM package, and let's say it is pooling, and then we have to use the command PLM, and we have to enter the data exactly as before, in the sense that we say investment is a function of capital and value, and the data is Grunfeld. Now note that here we have to add an additional parameter now, in the sense that we have to specify the model. And since we want to run a pooled OLS, where we ignore the panel structure, we have to enter pooling. Now, this data will give us the exact same result as before. Now, this is simply to show that despite the fact that you have transformed the data to make it specific to be used in the package PLM, you can still run a regular OLS regression. But of course, this is not what we want. We want to make sure that our model captures the fact that we have different firms over various time periods. So here again, we have the pooled OLS model, the results. But now what we really want is to estimate a fixed effects panel model. And so let me first talk a little bit about the theoretical concepts of a fixed effects panel model. Now here we say what we assume is that we have a constant slope of the coefficients. So there's a constant slope associated with value and capital across the firms, but this slope is going to vary based on, the slope is not going to vary, but it is actually the intercept which is going to vary. So note that we have here the notation I and T, where I refers to the individual firm and T refers to the time period. Note in this case we have a 20-year time periods, and we have 4 firms. And you can see that beta 1 and beta 2, the slope coefficients, are constant and do not vary based on firm or time period, but it is actually the intercept which is going to vary based on the firm. Note that this fixed effects model can also be written by including various dummy variables in the model. What those dummy variables do based on the firm is to shift the intercept. So basically, we are going to estimate a model where we have 4 different intercepts, but constant slope coefficients. Okay? So the intercept in a fixed effects model is going to be firm specific. Now, if you're thinking about this not in a firm context, but more of a people context, then think about that this specific intercept could be based on education or ability. Okay. Also note that the intercept is going to be time invariant, and that the slope coefficients do not vary across individual firms or time. Now, in order to implement this in R, again, you have to use the PLM function, and you have to actually specify the model as what is called within. Okay. Now, let's do this in R. So here, to make our life easier, we can copy what we have done before. And here we are going to just say fixed. And here we are going to say fixed, within. And here we are just using the fixed. Okay. So now here, lines 12 and 13 are now specifying a fixed effects panel model. Now note that the output of the fixed effects model is different compared to the output of the regular OLS model. Okay. The first thing you will note is that the intercept is gone. Well, we will soon see that the intercept or the intercepts are still in the model, but they're not reported in the output. We only have capital and value, the slope coefficients. They're still statistically significant, but note that their value has changed compared to the regular OLS model, which ignores the heterogeneity across firms and times. Okay. Also note that the R squared, or the adjusted R squared, has increased compared to the regular OLS model. If you want to know how the intercepts look like, what you can write is fixed, or fix EF, and you enter the model. In this case, we had B hat, GLM fixed, and now you have the 4 intercepts associated with the 4 firms, with firm 1, 2, 3, and 8. Note that you can replicate this exact same result by running a simple OLS model, but making sure that you implement the firms as factors. So you can write, for example, B hat. Let's call this OLS factors. This would be investment, capital, value, plus factor of the firms. And the firm and the data would be Grunfeld. Note that here you have replicated the fixed effects model with a regular OLS model, but you were able to do so because you have incorporated the various firms as factors, which means that those intercepts here, okay, you have the intercept for firm number 1, which is identical to what we have seen before. And if you want to calculate, for example, the intercept of firm number 2, you have to take the intercept that you have here plus 180.5. And what you would get is this intercept of almost 95. Okay, so it is a slightly different interpretation, but note that you still get the same coefficients for capital and value as you would get if you ran the fixed effects panel data model. Now, the question is, well, what really tells me that the fixed effects panel model is better than the regular OLS model or the pooled regression model? This test can be implemented with the function pf test, and you have to enter the fixed model first and then the OLS model. So when we do this here, we write pf test, and we have to enter the fixed model first and then the pooled model. Then note that the null hypothesis is that the OLS model is the better fit for our data, but you can see that since the p-value is below the threshold value of 5%, even at 1%, we reject the null hypothesis that the OLS model is better, and hence conclude that in this case it is more appropriate to use the fixed effects model. Now, this is the fixed effects model, but there's also a second type of panel data model, which is called the random effects model. Basically, what the random effects model does, it assumes that the firms that we have drawn are part of a much larger data set or much larger population, and that the intercepts that we are determining are actually random variables and not necessarily fixed variables as we have done in the fixed effects model. To estimate a random effects panel data model, what we do is we specify the model as random. So how we would do this in R, we say, let's call it random. Call this random. So when we execute the model, then again we get the slope coefficient associated with capital and value, and those are again statistically significant. Now the question is, how do we determine which model to use? Well, again, there are two additional hypothesis tests that we can do. Now, in the first hypothesis test, we are only going to focus on whether we should be using a random effects model or the regular OLS model. Okay? And to test the hypothesis that the OLS model is better, we can use a function which is called PLM test. And we enter the pooled model, so B hat PLM pooling, comma, type equals BP. Note that the BP refers to what is called a Broich-Pagan-Lagrange multiplier test. Now, what this model now tells us, based on the null hypothesis of no panel effects, that is, the OLS model is better than the random effects model. And we can see that, again, the p-value is below any threshold that we could conceivably come up with. And hence, we reject the null hypothesis that the OLS model is better. And hence, at least in this case, the random effects panel data is again better than the regular OLS model. So what we have seen so far is that if we run a fixed effects model and if we run a random effects model, and we are comparing those two models with our regular pooled OLS model, we find that it is better to use a panel data model. Now, the last test that we have to do is to think about, should we be using a random effects model or a fixed effects model? And again, there is a test for this, which is called the Hausman test. And it tests the null hypothesis that the preferred model is a random effects model. Okay. And here what we do is we use the command phtest. We enter the two models. So note that in our case, I have called this B hat PLM random and B hat PLM fixed. And here the null hypothesis is that the fixed model is better. Sorry, it tests that the random effects model is better. And if you execute this test, you find that it turns out that we reject that null hypothesis, and we fail to reject the null hypothesis, and hence the random effects model is appropriate. So this concludes the lecture on panel data.